Hi everyone, I'm Toon. I'm a security engineer at Sigma Prime. We're a blockchain security and R&D firm. We do security reviews, on-chain and off-chain stuff, and we've also got some cool projects like Lighthouse, the consensus client for Ethereum, and Anchor, the SSV client. So this is a talk I made on the Ethereum hard forks and how they affect smart contract security. And in focus, in particular, the Fusaka upcoming hard fork. So if you are a developer or a security engineer working on Ethereum smart contracts, and you have no idea what's in the upcoming Fusaka fork, this talk is perfect for you. All right, so we'll start off with an overview of the upcoming forks, sort of in terms of scope and in terms of timeline. Then I'll hopefully try to convince you why this matters, why you should pay attention to this. Then we'll actually dive into the changes in Fusaka. Then we'll have a look at Glamsterdam, which is the fork after Fusaka. And then hopefully we'll have some time left over for Q&A. All right, so currently we're on the Pectra fork. It was activated, I think, in May this year. It contains some cool features like account delegation with 7702. Then the next fork is Fusaka, which should activate it in, I think, a little under 2 weeks. It contains the major feature peer DAS. And then the fork after that is Glamsterdam. Okay, so why does it matter? Why should you be paying attention to these forks and their funny names? Well, the core problem here is that smart contracts are immutable, but the EVM is not. And that can cause issues. If we go, for example, with the Jenga analogy here, if your smart contract is on top and the EVM changes below, well, the stack might come tumbling down, and that's not great. The Ethereum core developers, they try really hard to ensure there's no breaking changes in each fork. But sometimes changes have to be made. And in such a case, it's really important to be aware of these changes and to take action if it's required. The great news here is that the changes in Fusaka are much less severe than compared to Pectra, for example. If you remember, in Pectra we had EIP 7702, which introduced delegate accounts, and that broke this check right here, message sender equals transaction origin. That caused a lot of issues. Many large Ethereum projects, for example L2s, relied on this check to ensure that a transaction was sent by a EOA, another smart contract, and this EIP broke that check. All right, let's dive into the actual changes into Fusaka. So first off, there's 2 changes to the mod.exp precompile. Mod.exp is a precompile for modular exponentiation. It's not used that often, but it's used in cryptographic operations. Most notably, RSA verification uses it. If you want to call mod.exp, you'll have to give 6 inputs, a base, an exponent, and a modulus. And each of these requires a length as well. And so currently on mainnet, these inputs cannot be of any arbitrary size. And as you might imagine, that causes a lot of difficulty for implementations. And as a result, mod.exp has been the source of many consensus bugs in the past. And that's why this EIP has sort of been, is now included in Fusaka. And the idea is that after this EIP is activated, each of these inputs must be 8,192 bits or smaller. So there's a limit on input size. Now that means that if your contract currently on mainnet relies on mod.exp with these large inputs, then that will actually no longer work after this EIP is activated. So if you send an input larger than 8,192 bits after Fusaka, the precompile will actually return an error, and it will consume all the gas. Which is not great, right? That'll basically cause DOS issues in your contract. The good news here is that the EIP authors did some analysis, and they found out that there's basically never been a successful invocation of MoneyXP with an input larger than 513 bits. So all in all, it's expected that this really won't break anything. The majority of the invocations even use size 32, 128, and 256 bits. So that's all in all quite okay. The second change to ModExp is a change to the gas schedule. The gas schedule was changed to this function. Now, I know it's kind of boring, so I won't explain it all. I'll give you the TLDR, which is that the minimum cost was increased to 500, the general cost was tripled, and there's an extra cost for large inputs larger than 32 bytes. So the impact here again is if your existing contract calls ModExp with a fixed gas stipend, well, then the gas stipend may not be large enough, and the invocation will actually run out of gas, causing errors and a revert. So this, again, can cause DOS issues for existing contracts that use ModExp. In general, assuming that any gas cost in the EVM is going to remain fixed is a bad idea. So you should really not assume fixed gas costs. The third change is the introduction of a gas limit cap for transactions. Currently, a transaction can basically take up the whole block, which is 45 million gas today. And after this EIP, a transaction will be limited to 60 million gas, basically decreasing the maximum size by 3 times. So the impact here is that functions that require a lot of gas may no longer be executable. To give a quick example here, the top function is a bad implementation. If the user array grows too large, then at some point the function is going to require much more gas than the 16 million limit and will be unexecutable because it will always revert. The second function is much better. There's a start and limit parameter, and as such, it can be called across multiple transactions. So this is a known issue for Ethereum, and we often see that for these kinds of easy view functions, clients do implement the second version, like the good version. But it's also important to notice for more complex functions like liquidations, for example. This should also be taken into account. You can maybe imagine if a user is liquidated, there are multiple positions, let's say, that have to be liquidated at once, and that may also cause these types of issues. So it's important to keep that in mind. Right, these last 3 issues were the only ones in Fusaka that will impact existing contracts. The following 2 will only impact new contracts. So there's a new opcode in town, CLZ, count leading zeros. It's a great opcode. It'll make some math and crypto operations easier. It allows you to count the leading zeros in a stack element. Now the issue with the new opcode is that L2s might not immediately support it. So for example, that's an issue when you deploy a contract which uses CLZ on a chain that does not support CLZ. So for example, let's say you have a contract with a deposit function and a withdraw function, and the deposit function does not make use of CLZ. Then users can just freely deposit money, everything will work. While when they call the withdraw function and CLZ is triggered, a revert will occur because the L2 does not support CLZ. And as such, funds will remain stuck in the contract. Not great. For now, Solidity does not support CLZ. There is, however, I think a pre-release version which does allow CLZ to be used in assembly blocks. But generally, it's not yet used in code generation. But of course, expect this to change. Then there's also a new precompile, the P256 verify precompile, which allows ECDSA signature verification over this particular curve. If you call it with a public key and a signature, it'll return 1 if the signature is valid. And similar to EC recover, it'll return the empty return data if the signature is invalid or if the inputs are generally malformed. So similar to the last issue, the problem here are L2s that don't immediately support the precompile. Currently, Solidity does not support P256, so you have to use a low-level call. Yeah, a note here is if you use a low-level call and the contract does not exist, for example, if the L2 does not support it, then the EVM will return successfully by default with no return data. So there may be some confusion there. All right, so those were the changes in Fusaka that will actually impact smart contract security. There's, of course, many other, most notably PeerDAS, which will increase the number of blobs available. And there's a lot of other changes as well. But again, these should not really impact smart contracts. So I'm not going to go over them. Nice. We can look forward then to Glamsterdam, which again is the fork after Fusaka, should be coming next year. Glamsterdam is currently has 2 headliners, EPBS and block level access lists. Neither of these should have any impact on smart contracts, which is great. And then there's many other proposed EIPs currently. I think roughly 50 are currently proposed. Of those, the ones that have any impact on smart contract execution, we can basically sort them into 3 major categories. That is new opcodes, new precompiles, and gas changes. We don't know, of course, yet which ones will actually end up in Glamsterdam, but it's pretty clear that some combination of these categories will end up in Glamsterdam. So again, for new opcodes and new precompiles, the potential issue there are L2s that don't immediately support it. So you have to watch out there. And then gas changes are a bit more tricky. And the key there is, of course, don't assume a fixed gas cost for certain operations in the EVM. That's really key. All right, so to sum up, being aware of these changes is really important. As you've seen, like these assumptions you might make during development of your contracts can really change after your contracts has been deployed. The good news here is that the impact in Fusaka is pretty limited, especially compared to Pectra, which was more severe changes. And then for Glamsterdam, we're not sure yet what's really going in the fork, but we can expect new opcodes, new precompile, and gas changes. So make sure to expect those. All right, do we have any questions? Feel free to put your hand up.
More of a general one, just myself. Are there any plans at any point in time to ever add back any of the EOA detection functionality that getting rid of tx.origin and message sender erased?
Yeah, great question. As far as I know, there's no plans. There is a new version of the check that can be used to still distinguish smart contracts from EOAs and smart accounts, which is basically adding the Xcode size check. So yeah, that's a way to still do this.
Hello, great talk. And I have a question about do you know how many attacks happened because EIP 7702 changed the security assumption?
Sorry, can you repeat the question?
Oh, how many attacks happened because EIP 7702 change assumptions?
Yeah, as far as I know, there's not been any actual attacks from these changes. But there have for sure been yeah, some projects have had to make updates to account for these changes for sure. Yeah.
Thank you.
Is there any way to know who the person that initiated the transaction initially, rather than knowing the contract address or a dedicate, to know who actually is the transaction origin starter?
Sorry, could you repeat?
Is there any way to know who actually initiated the transaction to the blockchain and be accurate that yes, it was this address?
So the question is, who initiates a transaction?
The question is, yes, to know if an address is actually the TX origin, regardless of these new changes. If I delegated to a different address, can you still know that it was me who started the transaction?
Yeah, transaction origin will still point you to the person who originated the transaction, for sure. Yeah.
Okay. Yeah.
All right. I think that's it. Thanks, guys.